So we are interested in the information associated with the variation in the data. If there is no variation in the data, that would be nothing for us. So what do you mean by the no variation is, let's say we have a certain number, so x1, x2, yeah, we are trying to predict y. But x3 is always 5, it's 5, 5, 5. If this is all 5 for all y's, what do we need this? I don't need this, right? That's why we can actually drop it, but that's the extreme case. If this is not no variation at all, but what if this is like a 4.9, 5.1, 5.0, 5.02, 4.97, and so on. It doesn't change a lot. It has a variation is pretty small. Then actually it might be, maybe we can ignore this variable also. So that's why we are looking for actually the changing the axis. Even though we are calculating here calculating the line, but actually we are tilting our axis so that this is the perpendicular to each other. And also same times we just find out the make our variables as maximum. So this is actually it has a higher variation than the fat only and protein only. So bigger variation, and then we find out small variation. So whenever we find out the one principal component, we will find out another small variance. Because this is just 2D, we can have only two. Again, 2D, we can have only two principal components. But when we have a multiple dimension, like a 7 dimension, then we can have also tilted 7 axis. So we will find out the PC principal component. This is just like can we our data itself is just stay the same, but can we move our axis so that our that new axis value will show the the biggest variation, and the other side is the smallest deviation, right? So direction where there is the most variation has the most information. So that's why we capture not only the original independent variable, can we create the new independent variable by tilting the axis, and can I capture the biggest variation? And using that's only one the principal component, still we can do way better than any other original, right? Visually, the line captures the largest amount of variability in the observation, right? And replace the both variable with the first component, principal component. Then we can reduce the one. You previously was a two independent variable. Now we are using only one independent variable. So think of the first principal component as a weighted linear combination of x1 and x2. So we are considering on the two-dimensional case the linear relationship between 1 and 2. Then we can capture, right? So linear combination of them will capture the relationship, and then we can find out the biggest variation and also the small variation. By applying the PCA, what we're gonna get is all the principal components are uncorrelated with each other. Here, even though I said uncorrelated, that does not mean the correlation is 0. So, but it will be pretty small correlation, so that we assume our principal components, none of them are correlated to each other. Okay. And previously it was like this, and then now we changed our axis here, so we just make it turn this way so that we can have a new variable PC1 and PC2, right? So PC1 has a more variation and PC2 is a small variation. And then numerically how the computer find out the principal component is calculating these things. Calculating this, right? The distance of our data to the new axis. This actually that's calculating the distance, and then we're trying to minimize. Okay, so we just keep rotating, and then find out summation of all the distance or the square, and we will find the line that has a smallest distance to the axis. Then we found the PCA. So observations has been rotated, right? So actually that's rotating our axis. So the first and second principal component directly coincide with the axis. However, this is the 2D case, but 3D, 4D, even 7-dimensional, yeah, we cannot draw. We cannot imagine the picture. However, it's still mathematically it's possible. Data has not changed yet, right? It's not changing. It's still there. We just change the axis. So we are calculating the new independent variable. Right? Position of the observation relative to each other remain the same because we are not actually changing the data. Yeah, we change the axis. We change the axis, and then we change the coordinate of our observation. Okay. So new axis is a more abstract and weighted linear combination of original variable. Okay. So I'm not talking about how we find out the principal component analysis, and then conceptually, I want to understand what the principal component is. Okay. So we can replace the both variable by the first principal component without loss of much information. Okay, so PCA is essential to the scale of the data, sensitive to the scale of data. That's why you better standardize the data before PCA. Yeah, so because the one x1, x2, x3, we have many independent variable. One of them has like thousands of the scale. It's 1,000, 2,000, 3,000, and the other one is all just like a 0.1, 0.2, 0.3. Then the PCA calculation can be affected by that scale. That's why we better do the standardized, use the standardized data, right? So that our PCA calculation will not affected by the scale of the data. Okay, so we find out what is a PC1 and PC2. So PC1, we can find out PC1, what would be the PC1. So this is okay, this is one observation. PC1 score, this minus 1.1910 is calculated by this one is a 0.707107 times fat okay plus 0.707107 times protein. Okay, so yeah, this is the one, but actually before this we use standardization. So Fed was a 6, we are not putting in this 6.5 or 1.5, we change, this is the standardized, right? And then we standardize this protein here, and then this number will go into the fat, and this standardized protein will go to there, and this calculation will be the PC score 1. So this one is for the 3 musketeers. This is the from here, the PC1, and then minus 7860 is come here, and this number is coming from here. Yeah, this is the same number, it's coincidence, but actually this number comes to here. And then using calculation, this is the minus 1.1910, which is this number. So we can change, instead of using fat and protein, we can use PC1. And we can do the regression using only one variable. We can use both of them, but still, yeah, we can use a new predictor, independent variable. Okay, if we have a k number of original data, then we can create it up to the k principal component. Again, this is just changing the rotating and changing the axis. So we are not creating the new data. So if you trying to create the more than k principal component, and then that will violate the condition. All the principal components are uncorrelated with each other. Once you create the more than k principal component, then one of them should be the linear combination of others. So it will be correlated. So amount of variance explained decreased as you go to the later principal component. So the order is important. First one is most variable, most has a highest variance, and then as small and small and small as the number goes. Yeah, that's why the first few principal components often represent a very large portion of the total variance. So we can just use the first few, then you can capture the most of the information. This allows us significantly reduce the number of dimensions. I don't have to use like a 4, let's say we have like a 10 independent variable, but if you use a component, principal component analysis, we can use only the 3 or 4 independent variable, we can reach the high R square. And the principal component is uncorrelated, so you don't have to worry about multicollinearity problem here, because we create the principal component in that way, it's not correlated.